Hello to my friends joining us via recording. It is May 1st and we are reviewing more for the final exam. So we have a lot of different topics that we mentioned we wanted to cover during our time today. So we're gonna bounce around and cover a whole lot of different things. One of the things I want to start with, because it was earliest in the semester, was talking about the difference between the two types of fat cells that we read about. So my friends here in class today, I know this is in lecture 1. Can you guys help me out? Where would I find these images and these questions in lecture 1? Is it that last page, I think, of lecture number 1? At the very bottom? Yeah, very last page. Perfect. Okay. So when we were studying, let's get big picture idea what we're talking about here. This lecture number 1 was all about anatomy versus physiology. Remember, our class was an anatomy and physiology class, and so we did a lot of comparing the anatomy of structures to their physiology, or comparing the physiology of structure to its anatomy. Help me out here in the chat. When I talk about the anatomy of something, what does anatomy mean? What am I studying in anatomy? Okay, yeah, so I like the way Eileen mentioned what it is, what's there. So anatomy. So when I'm looking at, I can see that I'm coming in and out. Now it looks like my back now. This is purple. See me. I just in and out. On my end, it's showing. Let's see. Can you hear me, or is it choppy? Ooh, okay. If it doesn't improve. Can you hear me, or am I still choppy? I know my video's not working. It's better? Okay. Maybe what I'll do is I'll leave my camera off for now in case that was jamming up my internet. And if it keeps giving us trouble, keep letting me know in the chat. If it gives us more trouble, I will try starting over. So we'll start over since it ate all of the writing on the board. But if it goes in and out again, please let me know in the chat again. Thank you for making me aware of that so I didn't go on forever without you hearing me. Okay, so let's add what we had before. We had anatomy versus physiology. And you guys told me that anatomy is basically what's there. What's there, what it looks like. It's all about structures. So I'm looking at the two kinds, a cartoon of the two kinds of fat cells in the body. The two kinds of fat cells that we had white, or let's give the technical name, adipocytes, and we have brown adipocytes. That adipocyte word is the fancy word for fat cell. So I've got white fat cells and I've got brown fat cells. I can tell from looking at the pictures of these two cells that they definitely don't look the same. So that is anatomy. When I look at them and I see that their appearance looks different, that's just doing anatomy. And remember, we said at the beginning of our semester, what we did in lab was a whole lot of anatomy. We don't do a lot of anatomy in lecture. We do a whole lot of physiology in lecture. What's physiology? When I talk about the other half of our class, what's physiology studying? Eileen's like, I'm much better at anatomy. I feel ya. Yep. We can memorize anatomy, right? We can just memorize what's there. When it comes to physiology, like what we're saying in the chat here, is that's what it does. What it does, or we could even say how it works. The physiology side of our class is what's its purpose? How does it get that job done? So these are things where the reason that it's harder for us to memorize it, right, is we have to kind of think our way through it. We have to understand physiology. We can memorize anatomy. So it's easier in that regard, figuring out what's there as opposed to how it works. When I talk about the relationship between anatomy and physiology, they are or are not related. Anatomy and physiology are or are not related. Yeah, they are related. The way that we described it way back in lecture number 1 is anatomy, the word is dictates or determines physiology. And we also said that the opposite was true too. We'll type that up. Physiology dictates anatomy. In easy words, that means that what's there in the body is going to tell me what it does. I can get clues about what it does. Physiology, so by what it does, can tell me what I need to have to do that. So anatomy dictates physiology, physiology dictates anatomy. We really can't study one without the other because they depend on each other. So we did a lot of examples in lecture number 1 of relating anatomy to physiology, and you'll want to go back and review those examples. Although, to be honest with you, I probably won't reuse a specific example from the lecture packets. So you want to be thinking about how we use those examples to illustrate these ideas here. That what's there tells me what it does, or what it does tells me what's there. So what we specifically did with brown fat and white fat, though, because that's one that I did tell you I could use this example again. We wanted to look specifically at some of the anatomy of these types of cells, and we also wanted to look at the physiology of these cells, what it is that they do. So let's see if we can remember way back from the beginning of the semester. Over here on the left, when I'm looking at this adipocyte, this fat cell over here, would I say that this one is a white fat cell or a brown fat cell? Which one do I see here on the left? Yeah, a couple of us have chimed in. This one over here on the left is a white fat cell or a white adipocyte. Yeah, Marilee says it's literally white. That's correct. Yeah, this one over here, when I look at it, I have this big white or beige space here in the middle. That is absolutely a white fat cell. When I look over here at my other fat cell, by process of elimination, we know that this one is a brown fat cell, right? Because that's all I have left. But we also can see that this one, its coloration looks a lot more brown. So this one is a brown adipocyte compared to my white adipocyte that I see on the other side. Now, let's see if we can remember, because it's been a while since we read about these cells. What makes this kind of fat cell over here brown are all of these little things right here. What are these little things right here? Do we remember from this article? What are these little brown guys right here? One of us remembers. Those are my mitochondria. Not a lot of space. I put too many things. So here I'm going to put it right underneath. When I look at that cell, all those little brown things equal mitochondria. These are my mitochondria. Yeah, you wanted to say that, but it's been a while. Yeah, that's okay. This is a safe environment to make mistakes, so I'm not going to make fun of you if you say something wrong. So feel free to guess, right or wrong. All of these little guys right here are mitochondria. When we talk about brown fat cells have a whole lot of mitochondria. Mitochondria, here's a tie-in to Unit 3. Remember that mitochondria we use to perform the electron transport chain, which is that process that we go through to use electrons that are inside our cell to make energy. So these particular brown fat cells have a bunch of these little energy building machines inside of them, all of these little mitochondria that are inside of them. So when we talk about the kinds of functions that a brown fat cell would be really good at doing, one of the things it's really good at doing is actually making ATP. I know this because it's filled with my ATP building machines that I see right here. It's filled with those mitochondria. But making ATP wasn't the main function that we studied when we talked about brown fat cells. When we talked about brown fat cells, does anyone remember what we said kind of their big picture purpose was? What was the purpose of brown fat in your body? It's been a long time, right? Let's see if we can remember. Yeah, so a couple of different things that are mentioned here in our chapter. First one is that they burn calories. Yep, so burning extra energy. The second thing, though, that relates to this burning calories has to do with what we might say their overall purpose is. And their overall purpose is to generate heat. That's their biggest picture goal. That's why, by the way, brown fat cells are so important in babies. Remember from Unit 2, when we talked about how the skin helps you with your body temperature. One of the ways that a baby is not so great at using its skin to sweat or to make those blood vessels smaller, but what babies have is a whole lot of brown fat. Brown fat helps to keep babies warm. So we see proportionally a lot more brown fat in a newborn than we would see in an adult, for example. And the job of the brown fat in that baby is to generate heat. Now, here's where we have to get to the application level with Dr. Aulis. I know you guys hate it sometimes where I make you go to the application level, but let's do application level together here. I am looking at a cell, a brown fat cell over here, and we say that the physiology of this cell, the job of this cell, is to make heat. That's what it's going to do in my body when it makes heat. What can that tell you about what happens when mitochondria are doing their job? Can we make any predictions here? This cell makes a whole lot of heat. It has a whole lot of mitochondria. Yes, so when mitochondria are burning calories, what must happen when they burn those calories? Yeah, it makes energy, but it's making something else too. Yeah, we see it when we exercise, right? What happens to you when you exercise? When we go outside and exercise, especially as it's getting warmer, we get really hot, right? Yeah, Ariel mentioned we start sweating. Hey, so check this out. When these mitochondria are doing their job, which is making ATP or burning calories, that process of, especially I like the word burning in its name, burning calories literally generates heat. So these cells, these brown fat cells in our body, their job is to generate heat. That's what we learned their function as. They burn calories and they generate heat. That's their physiology. So I look at their anatomy, and when it comes to things like burning calories, it makes sense. Yeah, my mitochondria, they burn calories to make energy for me. But what must also be true based on their job and based on their appearance is that mitochondria must also make heat when they're doing their job. because this cell has a whole bunch of mitochondria and its job is to make heat. So let's put this into the terms of where we started here. Anatomy dictates physiology. What's there tells me what it's going to do. When I look at a brown fat cell, I can see that what's there is a bunch of mitochondria. That tells me that this cell is going to burn calories. It's going to break stuff down. But I can also do the opposite. Physiology, what this cell does, can tell me what's there, or how that what's there is working. So I know that this type of cell burns calories and it makes heat for my body, which gives me an idea that all of these mitochondria that live inside of it, when they're doing their job, they must make heat as well. So we made a prediction about what this cell does in terms of the burning calories, the making ATP. We predicted that based on what was there. And then we used what we knew about its overall function to figure out how some of these smaller pieces worked, what their other job was. I need you to help me out in the chat here. What questions do we have right now? Or maybe let's put this another way. Can you re-explain for your neighbors what did we just say? Can we re-explain what we said? I wish we could just turn to a neighbor, right? That would be great. Okay, so somebody said mitochondria create heat, as well as the overall brown fat cell. So maybe we could rephrase that just a little bit. Mitochondria create heat, which contributes to the overall function of the brown fat cell. How about that? So mitochondria create heat. That's the job of a brown fat cell. I got a whole bunch of mitochondria. They must help me make heat. And yeah, Ariel kind of summarized it in big picture for us. The anatomy of this cell helps me to know what it's doing. So I have a bunch of mitochondria in here that helps me to know that this cell, like we said, burns calories or makes ATP. And we could predict from that, because my cell makes so much heat, that's its other function, that it must release a lot of heat when I do these processes here. We kind of like reverse engineered the whole process of using anatomy to dictate physiology. We started with what it does, then we looked at what's there, and then we made a prediction about how things work. So big picture, here's what we should be considering here with my brown fat cell over here on the right. First thing we should consider, make sure we know that this type of fat cell is really good at making heat. It's really good at burning calories. I saw earlier in the chat, it helps us to get skinny, right? These are the skinny fat cells, if you will. So first thing we want to know about brown fat cells, they help us to generate heat. Second thing we want to know about brown fat cells is what makes them brown. They're brown because of all the mitochondria. The third thing we want to know is that because these cells generate heat, that's their overall function, we must use what's inside the cell to do that. And what's inside the cell are all of these mitochondria. So if I know that this cell makes a lot of heat, and I know that it's filled with mitochondria, mitochondria must make heat when they're doing their job too, because something inside this cell makes it warm me up, and what I have inside this cell is the mitochondria. So Brown fat cells make heat. That's idea number one. Idea number two, they got a whole lot of mitochondria. Idea number three, mitochondria make heat when they do their job. Thumbs up, thumbs down. Where are we at? What are we thinking about this one? Okay, I'm getting some thumbs up. When I was in high school, I took a rhetoric class. I don't know how many of you guys ever had to take like a logic class or rhetoric class. They always use this little picture, right? Let's see if I can draw it. Where it's like the three-sided triangle or whatever. It's like, if you know this, then you know this, therefore know this. So what we just did was a little bit of logic there. This is why we said physiology was harder, right? Because we can't just memorize things. So we started with, this cell makes me warm. And then we said what's also true is this cell has a lot of mitochondria. And so then we got to the application of, therefore, this cell that makes me warm and has mitochondria, it means those mitochondria must make me warm. We did a little bit of logic there. So it's a little early in the morning for logic, but we just did a little bit of logic. So there you go. Got some logic going on here. When we go over to white fat cells, they are much simpler, right? White fat cells are the normal kind of fat cells. We find white fat cells all over the body, right? When we think about white fat cells, what would we summarize some of their jobs? What's the function of a white fat cell? This is much more basic. What's the function of a white fat cell? Yep, so one of their functions, these guys are a cushion. Cushioning, absolutely. Insulation, and also the big one, I would say, would be that energy reserve. Energy reserve. Where my friend over here was all about burning energy, was all about making you warmer. When we talk about white fat cell, especially when we're relating its anatomy to its physiology, with these white fat cells, their anatomy most shows me that they're storing energy for me. The reason I say that their anatomy most shows me that is this whole thing right here. What is this whole thing right here that I just drew a circle on? What is this? Does anyone remember? Yeah, all this right here is my lip, my lipid, excuse me, my lip. We're done for the day. This whole thing right here, this is a big, huge lipid droplet. This is a big, huge energy reserve. When your body's trying to store energy long-term for an extended period of time, it's going to store it as lipids. Here is a big, huge lipid droplet inside this cell. Now, it just so happens that when I've got a bunch of lipids inside a cell, that also makes it act as a really good cushion, gives me padding, right? That's what's so terrible when my little skinny daughter, right, who came on yesterday to say hi, when she slams herself down onto my legs and her little tailbone, there's no cushioning back there. So all these lipids act as a really great cushion because we've got these fats that are technically stored energy that provide a cushion or something to absorb shock. This cushion or this stored energy also helps you to preserve your heat. So it makes it harder for you to lose heat, but we're not making any heat. It's just helping you keep what you already have inside of you. If we were to predict the function though of this cell, the easiest prediction to make based on its anatomy is that it's an energy reserve because all of this right here is stored lipids. So function of this cell, storing energy. It stores energy inside this huge lipid droplet that I see right here, this big one. Over here, my brown fat cell, we've got a whole lot of little lipid droplets that I can see right here. If I store the lipid in little droplets, it's easier for my mitochondria to break it down and turn it into ATP to burn those calories. It's a lot harder to burn all these calories that are stored in a big droplet over here. So my anatomy and physiology relationship with the white fat cell is much less complex. It's much more straightforward. See all these lipids I got right here? Okay, my job in life is to store lipids, to store energy. That's what's going on with a white fat cell. So white fat cells, much more basic. They don't do a whole lot inside of you. Brown fat cells do a little bit more. Specifically, they're making that heat. And the way they do that is through their mitochondria that we see here. That's about the extent of what we did brown fat and white fat. If you still have some questions about brown fat, white fat, you can go back to that article that we read because it does summarize some of those important differences between the two. We just want to make sure that we can kind of compare and contrast them. So how is their anatomy different from one another? How is their physiology different? How do they function different from one another? Are we still hearing it, or am I choppy? Because my mouse froze. Oh, it might be back. Okay, we can still hear me, so we're good. It was choppy for a second. Yeah, I was wondering. I wonder if they're doing something on the internet in my neighborhood. Like they would, right? The day we're reviewing for the final exam, they would mess with my internet. So hopefully it doesn't get choppy too much more. So yeah, if we have time, Emily, we could do positive, negative feedback loops. Feedback. Okay. Pilar asked if people can see me. No, so I think my camera might have killed my internet at one point. I don't have my camera on right now. Maybe when we're done covering content, I'll turn it back on and say hi to show you that I am here. So you're good, Pilar. I'm not on camera right now. Okay, we wanted to cover brown fat, white fat. I think maybe what we'll do next, I had a quick request about those 3 tonic words, those concentration words, to help us review those. So let's do that really fast. The picture you guys have in your notes looks like this. Oh, see, again, when I try to use technology is like, I mock you. One more time, try this. Nope. Okay, I'm just gonna hand draw it. Here we go. Big circle looks like this. This is a red blood cell. Red blood cell. Can anyone remind me? I'm guessing this is probably lecture 3, where we talked about hypertonic, hypotonic. Maybe it's number 2 actually. Hypertonic, hypotonic, isotonic. Okay, so Eileen's saying it's in lecture number 2. You got your red blood cell, and I believe on the inside it says the page 7. Perfect. The concentration of NaCl is, and then you got a big blank, right? And then we've got all kinds of solutions on the outside. So we got 0%. I'm going to put them in the wrong order probably. I apologize. 0.9%, 0.45. And what was my last one? Was it 4.5%? I can't remember what that last one was. Not that it really matters. We'll call it 4.5%. Saline. All these are saline. 3.5%. Okay. Okay, so we talked about our words that we used here. We used the words hypertonic, hypotonic, and isotonic. These are the words that we used. Remember when we were talking about these words, this word tonic right here always means concentration. So when we are comparing solutions to each other, we always use tonic words to compare them. If I'm talking about a solution that is hypertonic to another one, if I am hypertonic, what does that mean about my concentration? Hypertonic. Does anyone remember? Yeah, Eileen's questioning it. She's right. It is correct that it is higher. So hypertonic means that it's more concentrated, or it has a higher concentration. Hypertonic, a hypertonic solution is one that has more of something inside of it than the other solution. A hypotonic solution is the opposite of hypertonic. Yeah, so a hypotonic solution is going to be one that is less concentrated, or it's going to be one that has an overall lower concentration, meaning there are fewer things that are dissolved in a hypotonic solution. It has more water, basically. A hypertonic solution is going to seem like it has less water because there's more stuff dissolved in that water. Now, when we use the terminology isotonic, what does isotonic mean? What's going on with concentration in isotonic? Yeah, that iso part means that it's the same concentration or it's an equal concentration. Equal concentration. In our body, isotonic is best because if things are concentrated the same amount, we're not going to gain or lose water in our cells. Because see, the problem here when we're talking about hypertonic and hypotonic solutions is that if my concentrations aren't equal, naturally water is going to want to move. The goal of your body, Mary Lou mentioned homeostasis. Yeah, homeostasis is balance. That's the goal of your cells. Our cells want to be equal inside to outside. So if you remember, we added this to our notes somewhere around this picture here. We said the goal of diffusion and osmosis is isotonic solutions. Isotonic solutions. If you didn't write this down before, we want to write this down now. Or we might want to write it down again to make sure you remember. The goal of diffusion and osmosis is to make things equal. Now, equal is not always good because if we're talking about putting a solution outside your red blood cell that's really, really different from what's going on inside your red blood cell, that can be problematic because your blood cell might get too much water or it might lose too much water, depending on what it has to do to get equal to its environment. So when we talk about the best example of this isotonic, hypertonic, hypotonic stuff, it comes down to talking about the concentration of saline or salt, basically, in your plasma. So let's check out our notes. In your notes, help me out. Inside a red blood cell, what did we say is the normal saline concentration inside the cell? What's the number here inside? Yes, lots of us chiming in. The number here on the inside is 0.9% saline. 0.9. This is normal. So we look at the water inside your cells. We see how much of it's salt, how much salt is dissolved in, 0.9%. This is what is normal inside of you. So when we're looking at these solutions that we have here on the outside, we got a 0%, we got a 0.45, 3.5, and 0.9 down here. 0.9 down here matches 0.9 right here. This solution here in the bottom left, my 0.9, circle it. This one is isotonic because it matches the concentration of the amount of salt and water that's inside the red blood cell. So if you remember when we were working on this activity, we said that if I'm in a solution that is isotonic to me, if my concentrations are the same, the amount of water that goes in to my cell, there's my water going in, is equal to the amount of water that goes out. In other words, my cell is happy because I have the same amount of salt inside as I have outside. We're in an isotonic solution. My cell stays the right shape. It can do the right job. We're happy here. Now let's go over here to 0.45%. I know it's not a math class, right? We're not in math, but help me out here. This number over here, 0.45%, this is higher or lower than what I have going on inside the cell. What is this one over here? Yeah, it's a lower concentration, right? The amount I have is less. So we'll color code this one yellow over here. This is a solution that has a lower concentration. So when I look at my tonic words over here, I would say this is hypotonic. Hypotonic means the concentration is lower. Now, if I have a hypotonic solution out here, if we've got a hypotonic solution, who remembers what direction is water going to move if there's a hypotonic solution here on the outside? Does water go in? Does water go out? Yes, we're all agreeing here. Water is going to go into my red blood cell. Because when I'm looking at this solution here, it looks like there's way more water on the outside than there is on the inside. And remember, diffusion, and specifically when we're talking about water moving here, we're talking about osmosis. In osmosis, water moves to where there's more salt. So lots of water here on the outside, more salt comparatively on the inside. Water is going to go into this cell. And if you remember some of the pictures that we have in that notes, that causes this cell to potentially explode. If it gets a ton of water inside of it, it might explode. So if I put a 0.45% saline solution around your red blood cells, they might, yeah, the word that we used was swell, or they might expand to the point where they would burst. That would be especially true when we talk about this one over here, when we talk about pure water where there's no salt at all. If I were to put pure water around your red blood cells, which way is water going to move? Into or out of the cells? If we put them in water. Yeah, a couple of us agree. I promise it's not a trick question. Water is absolutely going to move inside. In fact, when we were talking about putting pure water outside your cells, we drew multiple arrows, putting that water on the inside. Because there's no salt on the outside, and this water sees all of this salt on the inside, and it says, well, shoot, I want to be there, and tons of water rushes inside. So this is, yeah, it goes at a much faster rate. This is when we read the article about water intoxication, and we talked about like hyponatremia. Hyponatremia is when we get below our normal salt concentration in our plasma. Whether we get to half the normal, whether we get, I mean, it'd be really hard to get down to zero, but wherever we're getting to, if we have too much water on the outside, that's going to cause water to go into my cells. And when water goes into those cells, they swell, they get bigger, and that's bad news for my body. We have this other solution over here, 3.5% sodium chloride or saline over here. 3.5%. Is that higher or lower than 0.9%? Yeah, trick question. It is math, but it's not tricky math. This is a higher concentration than what's inside the cell. This solution is hypertonic. It has a higher concentration. If I have more salt on the outside of my cell, which way is water going to move if I put that cell in a 3.5% solution? Now that water is going to go the opposite direction. Now that water is going to leave the cell. Because see, it looks like I have a lot more water on the inside of this cell than I have on the outside when I put it in a 3.5% saline solution. Yeah, so what I'm going to do is steal water from my red blood cell to try to get the concentration inside to match the concentration outside. I am essentially dehydrating my cells. Yeah, I'm stealing water from my cells to try to make them match. So best case scenario, we match at 0.9%. This is if you go to the emergency room because you've been vomiting, for example. We've lost a lot of fluids. A lot of times they'll just hang 0.9% saline just to get the volume of your blood back up to normal. We wouldn't want to give you 3.5% saline because there's way too much salt in here. Now, unless you were, water intoxicated, right? If we drank way too much water, we might give you something that's hypertonic to try to pull some of that extra water out. But in general, hypertonic solutions, they're going to dehydrate you. When we talk about solutions that are hypotonic, they would potentially overhydrate you. An isotonic solution, those cells stay the right size. They're happy and they're healthy. Somebody put in their anatomy for baby books, I loved this, for isotonic, when they were describing it, they said the cell says, I so want to stay at this concentration. I loved that. I so want to stay at this concentration because it's perfect. Isotonic, this is where I want to be. So isotonic solutions match. Hypertonic solutions are more concentrated. Hypotonic solutions are less concentrated. As you're reviewing this kind of stuff for the final exam, this would be the picture I'd say to go back to, because this summarizes everything we talked about. Hypertonic, hypotonic, isotonic, that kind of stuff. Give me a thumbs up, a dance party, a question. How are we feeling about these tonic words? Here, I'll give us our daily penguin while we're thinking of questions or we're finding the perfect emoji to express ourselves. The frog. Hey, by the way, I thought you guys should know, for those of you that were here early yesterday and got to see my daughter, she really loved it that you guys all sent her emojis. That made her day. But she also said, why did no one turn their camera on? So I'm just saying, guys, on Monday, I need you to turn your cameras on at the end of class, just long enough for us to raise our cups together for her to see you. Because she asked me lots of times. She said, why did no one turn their camera on? And I said, well, they were still in their pajamas. But maybe on Monday when we do our last hurrah together, we can turn on our cameras for like 10 seconds. Raise our cups, wave it at my little girl, and then you can turn your camera back on. It's okay if you look homeless, Eileen. If I wasn't going on camera, well, which I guess I'm not right now, right? But if I wasn't going on camera, I definitely would not be doing my makeup every day. Just saying. I do that for you guys, all for you. So, okay. Next thing, I think, let me go to my list of things here. We almost talked through, we got through transcription yesterday. Let's talk about translation, and we will use that then to talk about the levels of protein structure, because somebody asked us about protein structure here. So we're going to switch gears to Unit 2 to talk about the process of translation. Then we'll go through and talk about protein structures, and then we'll get into the types of cell junctions, those feedback loops, that kind of stuff there. Yeah, I think it's going to be lecture number 5. Let's find the lecture that had this picture in it. I'm pretty sure it was the one that was called the Central Dogma. It's the one we were working out of yesterday. Okay, lecture number 6. Yeah, so we're actually in lecture number 6 now. That makes sense. Yep, lecture number 6. Okay, let's remind ourselves a little bit of what we talked about yesterday. Remember yesterday that we said the central dogma, I take my DNA, which is my genetic information that tells me everything that happens in my cell, and ultimately I turn it into a polypeptide, or I turn it into a protein. So the central dogma helps me to take my directions and turn them into something that I can use. We talked about yesterday how I have to do this in 2 steps. I have to do transcription and translation. So when I'm talking about the central dogma, when we start with the process of transcription, remember that transcription takes that DNA message and turns it into RNA. Can anyone remember, why is it a good thing for us to build RNA? What is different about RNA compared to DNA? Can we think about why we need transcription? Or maybe I'll give you a better hint here. Where do we find DNA? And where do I find proteins? I know we talked about it in those terms yesterday. Yeah, DNA lives in the nucleus, right? Your DNA, your blueprints for everything that happens in your cell, only happens inside the nucleus. That's the only place that I'm going to find DNA. That keeps it safe. I build my proteins at ribosomes, and ribosomes don't live in the nucleus. So I have to get my directions from the nucleus out to the ribosomes without damaging them, without risking them getting exposure. The way I do that is I make this copy of mRNA. So the reason we do mRNA, or we build mRNA in the process of transcription, is to get a copy of our directions out of the nucleus. These directions leave the nucleus, they go to a ribosome where I turn them into a protein, where I can turn them into a polypeptide. We covered the process of transcription in depth yesterday, so if you didn't get a chance to attend yesterday, check out, or haven't watched those office hours, check those out from yesterday, April 30th. We talked a lot about transcription. Where we ended our discussion yesterday was right about here. So we were talking about how we built, let me zoom in, a strand of RNA. We built a message that can leave the nucleus, and we were going to send it out of the nucleus to help us make a functioning protein. So here's what we're going to pick up with this RNA leaving the nucleus. When RNA leaves the nucleus, it's going to the ribosome. So it's going to the place inside the cell where proteins can be built. Can anyone help me out in your packet? What page is this picture found on? Where's the ribosome picture found on? Okay, I'm maybe hearing page 5 in that packet. So somewhere around page 5, you've got, yeah, pages 4 and 5. Perfect. Okay, so you've got where we start talking about the process of translation. The goal of translation is to take us from the language of mRNA, the language of directions, and turn that into the language of proteins, something that's actually going to do its job. So my ribosome attaches to mRNA. Remember that the ribosome tries to read that mRNA, but it's an early reader. It's still learning how to read. So it reads things 3 bases at a time. Does anyone remember the name for 3 nucleotides at a time? What are those things called? 3 nucleotides at a time. Yeah, those things are called codons. Codons. I can only read in codons in little 3 bases at a time. Part of that comes from, if you look over here, here's my tRNA molecule. So we have multiple types of RNA in the cell. This one over here is called tRNA, and remember I told you guys to call it translator RNA, because it's easiest to remember. Technically, in your other science classes, we're going to call it transfer RNA. So to be technically accurate, there you go. My translator RNAs, they match up with, or they can read 3 nucleotides at a time. So this ribosome attaches to this piece of mRNA. It starts to look at the letters, the bases that are inside this message. So it looks at the bases and it says, I'm going to make this up here, AUA. It reads that. This one says AUA. And remember the example we said is we call out to the environment. We said, okay, guys, we got AUA. Who understands what AUA is? And we've got a tRNA molecule over here that says, oh yeah, I know what AUA stands for. Here's the amino acid you're looking for. So this tRNA molecule comes in and it brings its amino acid with it. That amino acid then is going to be added to this chain that we see right here. All of these amino acids in this chain are being put together by the ribosome based on what the sequence here was of the mRNA. So my ribosome goes through, it reads these bases 3 at a time, calls out the message to the environment, says, hey, does anyone know what this means? Can anyone help me figure out what's going on here? So we end up with a process that looks like this. Here's my mRNA message with all of its little codons that we see here. Here are the tRNA messages that understand what this mRNA means. Now, remember from class, I'll point this out for you, when we're looking at this picture and when we're practicing doing the process of translation, we only care about the sequence of the mRNA. We only care about these bases right here. These are the ones that matter to us. I don't want you to confuse yourself with these letters right here. These letters show you why certain tRNAs can understand mRNA. There's this terminology, and if you're really bored and you really want to learn more, it's things called an anticodon. I'm not going to test you on that. We're not really going to talk about that, but in case you're wondering what these letters are right here, they're called the anticodon. They help this tRNA molecule translate what mRNA is saying. When we do the process of translation, when we're trying to go and figure out what amino acids go places, we're just going to look at the mRNA. We're going to look at the sequence that we see right here. When we do the process of translation, just like those tRNA molecules, we just look at things 3 letters at a time. So we look at the first 3 letters, A, U, G. Now that I found these first 3 letters, I'll use that with the table we'll look at here in a minute to help me figure out, okay, the amino acid we're looking for is methionine. And then I'll go to the next codon, CCA, and I'll look at my table and I'll see, okay, the amino acid we're looking for is proline. So we read mRNA 3 bases at a time, those codons 3 letters at a time, to help us figure out which amino acids should be in our chains. By the way, I mentioned this yesterday, and I'm going to mention it again for you really fast. Let me see where that picture is. We looked very briefly at this little thing right here, where we took the DNA and we turned it into RNA. On the exam, expect to have a question where you're going to have to do a little bit of typing, where I'm going to give you a sequence of DNA like this, and I'm going to tell you to make my complementary RNA, or I'm going to tell you to make the complementary DNA. So please be prepared to do that. Type very slowly, check yourself. I want to make sure that you understand if I am trying to do the process of, this shows me the process of transcription, I need to understand that if in the DNA molecule there's a T, in the RNA molecule there's an A. I remember we talked about this yesterday. If the DNA molecule has an A, then my RNA molecule has a U, because RNA can't have thymines. So again, to reiterate, on the exam that we're taking on our final exam, make sure you'd be able to do this. Do the process of transcription, turning DNA into RNA. And I mentioned it yesterday, say it again, there's that transcription and translation practice worksheet. Please print that out and do it again, because it's been a long time since we last did that. And it would be great practice for you to help you with that kind of question. So expect to have to do the process of transcription and expect to have to do the process of translation. 100% I will give you this table on the exam. So remember, I've told you in class, and I'll say it again, that you do not need to memorize this table, but we do need to know how to use this table. So I'm going to make up a sequence here really fast. It could be completely not legit, so I apologize in advance if it's really terrible. We'll see how this goes. Okay, let's say that we are taking the final exam, and this is the mRNA sequence that I give you guys. When we go to translate the mRNA sequence, this is the table that we would use to do it. So I know it's been a long time since we did this. Let's talk through how we use the table. Over here on the left side of the table, we have the first letter in a codon. Along the top side of my table is that second letter in a codon. And then if you really want to, you can use this other side of the table for the third letter, or you can just be looking for yourself. So the first thing I would recommend that you guys do, and for the final exam, just like other exams, you are allowed to have a piece of scratch paper. So totally, I'd say the first thing to do when you see this sequence on your screen, get out your scratch paper. We need to divide this into codons. Remind me with codons, how many letters are in each codon? How many letters are in a codon? Yeah, a couple of us are telling me. I promise it's not a trick question. There are 3 letters per codon, right? So first thing I want you to do on your paper when you're working on stuff is go through and divide it into codons. Now that I have it divided into these groups of 3, now I get to start using the table. So we go over here to the left side of the table. The first letter in my codon is A. Okay, I got an A. I know I'm somewhere in this row right here. What I'm looking for is somewhere here. Second letter in my codon is a U. So I go to the top. U is this column right here. So this column goes down. We know that we were in this row, so I'm somewhere in this box. You can either then go all the way over to the side and figure out that G is on the bottom, or you can just look in here and see that G is on the bottom. Okay, so if I'm doing the process of translation, the first amino acid that this sequence called for was the amino acid methionine, MET. I got one amino acid down from one codon. Now I go to my next one. My next codon is UA. So we'll go over to our table. U, my first letter, I'm somewhere in this row right here. My second letter is also a U. I'm in this column, which means we're in this box. And it's UUA. There's my A. So my second amino acid in this chain is a leucine. My second amino acid is leucine. Okay, let me make you guys do a little bit of practice here. I want you to use the table. We need to figure out our last 2 codons here. Which amino acids am I putting in based on my last 2 codons? Yeah, so a lot of us are honing in on my first one here. GCA, G on the bottom, right? C in this column here, and A is alanine. So we got alanine, that's our next amino acid. And then a lot of us we're honing in on the last one too. CGA. Again, now we go back, so here's C. Go over to my G, and we got the A right there, CGA. That's arginine. Okay. On the exam, expect to need to do this. Again, transcription and translation practice worksheet is going to be a great way to practice for this. So for these kinds of questions, yeah, it's not too bad. It just take your time with it. Check your answers. Make sure you're going slow. It's really not that bad to take this sequence right here and turn it into a amino acid sequence. What we just did was we translated this sequence. We took it from the language of RNA and we turned it into the language of amino acids. Let me see, I got a couple questions to peek at here. Deepa asked, there might not be a stop codon in the sequence. Is that correct? And yes, that is correct. I may or may not put a stop codon. If there is a stop codon, what happens at a stop codon? Who remembers? What happens at a stop codon if we bump into one of those? Maybe we don't remember. It's been a while. Yeah, Pilar's right. Eileen's chiming in. A stop codon literally means stop. This is the message or a codon that I use to tell my ribosome we are done translating. Nothing after this point. So if you remember the example we gave in class, a ribosome hits a stop codon like this one right here, UAA. Ribosome bumps into UAA and it calls out to the environment, hey, who understands what UAA means? And then we got the crickets. No tRNA molecules can understand that one. It calls out again, UAA. Come on, which amino acid do we need here? Crickets. Calls out maybe one more time, and when nobody tells the ribosome what UAA means, it literally splits in half and we're done. We stop translation. So if we happened to have a stop codon in the middle of a sequence like this up here, we actually wouldn't translate the codons that come after it. Because when a ribosome hits a stop codon, it's done. Any more messages. So that there could be a stop codon somewhere in the sequence. There could be a stop codon at the very end, or I may not give you a stop codon at all. Many of the proteins in the body are millions of amino acids long. So if I'm having you just translate a little 5 to 10 part, 5 to 10 codon sequence, you may not bump into a stop codon. But be aware of that. If we hit a stop codon, after that point, there's no more amino acids. We don't do translation anymore. So if there is one, we'd stop writing. That's correct. If there is one, what I would perceive, what I foresee this kind of question being as, you know how when you have a question where there's a drop-down menu with the options underneath it, what I would see this question being as is you're going to have a series of little drop-down boxes. So we'll have little boxes here, and those boxes will have all of the names of the amino acids on it. So you'll go and put an amino acid, So you wouldn't be typing it. You would just be selecting the amino acid from the list. You'll also see stop, or you'll probably see one that says something like no amino acid, would be my guess. And I'll make sure to specify that in the question. No amino acid would be my guess as to what you'll see. So you'll see each of these little abbreviations. So it'll say Phi, it'll say Lu, it'll say stop, and then you'll see one that says no amino acid. That's what you can expect. I'm not going to make you go through. There's way too much margin for error, right? For accidentally typing ARP instead of ARG. I'm not going to make you type all of these. I will make you type your answers for doing the process of transcription, but I'm going to give you those little drop-down boxes to help you out with translation. So I think I answered the question, but I'll just mention again, Eileen asked if there's a stop in the middle of our sequence, we stop there. You stop there, but then you'll have an option on the drop-down menu for no amino acid. So for example, if this one right here was a stop, we'd highlight stop in this box, and then any boxes after that, you would put no amino acid. Just to clarify that we stopped here, didn't add any more amino acids after that. So no more using the table after that point, put it that way. Yeah. I think that's all. Let me check my notes to make sure. I think that's all we covered with transcription translation. Any other questions about the process of translation? or the process of transcription. Yeah, the last page talked about sickle cell. So go through and look over sickle cell anemia. Remember, the problem with sickle cell anemia is if we mess up the codon that we're reading, that can mess up the amino acid that we put in. And if I mess up that amino acid, that can change everything and give me all kinds of problems. So do review sickle cell anemia. And actually, it's a great transition for, let me go up to my protein shapes here. Great transition to help us talk about our proteins. Let me find the best page to land on. I didn't pull all of my pictures. So here, I'm gonna start because this is the only protein I have that shows me, or the only picture I have that shows me a protein that's folded up here. Okay, so this is probably lecture 5 now, talking about that protein structure. Yeah, so lecture number 5, around page 4. We're going to bounce around. We'll go back toward the beginning again, too. But what we're looking at right here is a protein that's folded into its normal 3D shape. When I talk about the normal 3D shape of a protein, which of my levels of protein structure is the normal 3D shape? The normal, type it out, normal 3D shape, and I'll put a note here of 1 amino acid chain. Yeah, you're lighting up the chat for me. That's called the tertiary structure. Tertiary structure, didn't spell that right, tertiary structure of a protein. Remind me, proteins do or do not need to have the right shape to do their job. Proteins do or do not. Yes, they absolutely do. That's the first thing we talked about today, right? Anatomy and physiology. I've got to have the right 3D shape to be able to do my job. Hey, by the way, hemoglobin is actually made of 4 amino acid chains that all have to have the right shape. What's the name, the level of structure when I have more than 1 amino acid chain that connect to each other? Multiple amino acid chains. Yeah, a couple of us chimed in here. The highest level of protein structure I can have with those multiple chains, it's called quaternary structure. Quaternary structure. If I were to put multiple of these proteins together, I would generate a really big functional protein that has quaternary structure. And that, by the way, oh yeah, there you go. So Pam mentioned that was in the final wiki. Yes, I did ask you about protein structure, didn't I? So quaternary structure, when we talk about huge proteins like hemoglobin, for example, I have to have more than 1 amino acid chain that are connected to each other. Each of those amino acid chains has to have the right 3D shape by itself. Because remember, the problem with sickle cell anemia is that a couple of my chains that make up this really big protein structure, a couple of them are shaped wrong. 2 of them are right, 2 of them are wrong. The 2 that are wrong make it so that my protein can't do its job. So 3D shape of 1 chain by itself, that's the tertiary structure. Quaternary structure is when I put more than 1 chain together. Since we're here, and we're looking at the picture here, this sure shows me how I form my overall 3D shape of proteins. Help me out with how I form the shape here. Which part of an amino acid do I use to help me form this tertiary structure? What are these parts that I see right here called on an amino acid? Do you remember what these parts are called that stick out, amino acid? Yeah, so these parts, our technical name for them was the R groups, or the word for them is the functional groups. Functional groups. Functional groups, if you remember back from this, the functional groups were what we called the personality type of my amino acids. Some of my amino acids are hydrophobic. Hey, we talked this yesterday. Hydrophobic, how do I feel about water? If I'm hydrophobic, what's my relationship with water? Yeah, that's a no-go. I like that. I hate it. I'm afraid of it, right? Okay, so some of my amino acids, their functional group, their personality type is we hate water. So these types of amino acids would squeeze together next to each other to push any water out. So some of my 3D shape of a protein comes from we're squeezing together things that all hate water. Some of my 3D shape comes from amino acids that can form hydrogen bonds. Now, we talked about these guys yesterday. I've got this little weird D thing with a minus and this D thing with a plus right here. What did we call these areas of partial positive or partial negative? These little D things. I might have seen someone chime in with it. Yeah, I think got a couple of us that remember. These little things right here are what we call dipoles. Dipoles. And remember, dipoles form when we don't share electrons equally. So some of my personality types don't share electrons equally, which means that when they get close to each other, they form these really weak, I put bonds in parentheses. It's just an attraction. Oh, you're partially negative, I'm partially positive. Let's connect, kind of. Hydrogen bonds. Some of my functional groups have a sulfur in them. If they have a sulfur, they can attach to each other really strongly. These, remember, are nonpolar covalent bonds. Covalent bonds were always the strongest type of bonds, and especially the nonpolar ones. They're really, really strong. So nonpolar covalent bonds, sometimes my functional groups connect with each other in really strong, we share equally ways. If that's the case, this part of protein structure is locked in place. And some of my amino acids have a positive or a negative personality. And if that's the case, we also can form an ionic bond. Big picture idea, though, from what we're looking at right here, is when we talk about tertiary structure, it's all about those functional groups. It's all about the personality types of the amino acids interacting with each other to give me this 3D shape that I see, that a protein has to have correct for it to be able to do its job. Now, contributing to this 3D shape, we also have things like you see right here, my orange curlicue ribbon or my blue flat things that I see right here. We talk about these orange curlicues right here. Does anyone remember what we called these that I'm looking at right here? What is this an example of? Yeah, it's one of those alpha things, right? My alpha helix that I see here. And then back behind it, we've got the beta sheets. So let's go back to talk about those guys right here. Ooh, those pictures copied funky. Sorry, guys. Alpha helix and beta sheet. An alpha helix looks like the curlicue ribbon that I see right here. So an alpha helix forms when my amino acids interact with each other in a circle. A beta sheet is gonna form when they interact with each other more on a flat plane or kind of a flat surface. When I talk about this kinds of things, alpha helix and beta sheet, what level of structure are we talking about now? An alpha helix and a beta sheet. Yeah, this is that secondary structure. Secondary structure. Alpha helix and beta sheet. When we talk about the secondary structure of a protein, what helps us to hold together the secondary structure is not those functional groups. It's not the R groups. It's actually the amine group that I see right here with this NH. And it's the carboxylic acid groups that I see with the COs. So my carboxylic acid groups interact with my amine groups in other parts of the chain. That leads me to fold these areas where I've got the curlicue ribbon to here, or where I've got these flat, almost accordion-like structures that I see here. So if we're saying that tertiary structure forms because of the functional groups, we would say that secondary structure forms because of things called the amine groups. That's the NHs. And the acid groups. That's the COs. Secondary structure forms from the amine and the acid group. Tertiary structure forms from the functional groups. So remember, you've got a compare and contrast table in your notes. You know Dr. Allis loves her compare and contrast questions on the exam. So important thing for us to compare and contrast the parts of the amino acid that would be involved. Let me see, I had a question. If I just said amino acids, would that be the same? Would not be the same, because an amino acid is the entire structure. Here, let me pull up a picture that we started with when we did this lecture in class. When I talk about an amino acid, this whole thing is an amino acid. So the amino acid includes the amine group, it includes the acid group, it also includes the functional group. So we have to be a little bit more specific. Is it the amine group over on this side that we're talking about? Is it the acid group over here? Is it that functional group? Because the question would be worded, which parts of an amino acid are involved in forming, and then pick your level, primary, secondary, tertiary structure, etc. So we have to pick specific parts to help us answer that question. The amine group, the acid group, the functional group. The most basic level of protein structure is its primary structure. So here's an image that shows me the primary structure of a protein. Make sure we know for proteins that what holds them together at the primary structure level is peptide bonds. Remember when we did this in class, we said anytime you hear this terminology peptide bond, we are automatically thinking protein. So peptide bonds only found in proteins. It's between the acid group of one amino acid and the amine of the other. I connect those things together to make this big long chain of amino acids. That's what my primary structure of a protein is. True or false? If primary structure changes, secondary structure changes too. True or false? Yeah, a few of us have chimed in. That would be true. The big idea for you to consider with proteins overall, if I change any level of protein structure from beginning to end, any level gets changed, that's going to lead to a change in the levels above it. So if I mess up my amino acid sequence, then I'm going to mess up the way that I make my alpha helices and my beta sheets. They're not going to form right because I messed up my sequence. And if I don't make my alpha helices and my beta sheets right, I'm not going to fold them up in this 3D shape right. And if I don't fold them in the 3D shape right, then I'm definitely not going to be putting together those pieces correctly. So I have to have every single order correct. Yeah, Mary Lou is absolutely correct. The example that we looked at of this that showed us every level's got to be correct was with sickle cell anemia. Because sickle cell anemia, we start all the way down with a problem at primary structure. I trade out one of those amino acids, and it just so happens that that amino acid went from one personality type to another. Remember, we have lots of different personality types. We've got some that are nonpolar, some that are polar, some that are negatively charged, some that are positively charged. Here's your reminder that I will not ask you to memorize which type of amino acid is what. I will tell you that information. But we do want to know that an amino acid that is nonpolar is going to act very differently from an amino acid that is polar. This is a review from yesterday. This nonpolar word right now, when we're talking about it today here, this nonpolar word, what's some synonyms for nonpolar? What means the same thing as nonpolar? Yeah, so it's equal sharing. These guys are going to share their electrons equally. Yep, the big one is that we're hydrophobic. Hydrophobic. Hydrophobic things hate water. They share their electrons equally. That's why they hate water, because water's got positives and negatives, and I don't need that kind of negativity in my life, or I don't need that kind of positivity. I got no charge. So nonpolar amino acids are hydrophobic. I am not going to find those anywhere where there's water. Remember, these were the ones that like to squeeze together. So they squeeze together to push the water out. Hydrophobic or nonpolar amino acids. Polar amino acids, they would or would not like to be around water. What do we think? Polar would or would not? Yeah, the polar ones would. Polar ones, we can use our other hydro word, right? Hydrophilic. These ones love to be around water because they have, this polar word, remember, means they have dipoles. They like to be around water. So hydrophilic and polar, same thing. Hydrophobic and nonpolar, same thing. Hey, help me out. When I'm looking at an amino acid with a negative charge, a true negative charge, or an amino acid with a positive charge, these would or would not like to be around water. What do we think? These would or would not like to be around water. You can totally guess. It's a no judgment zone. Here's our question. Negatively and positively charged amino acids would or would not like to be around water. When I talk about water and deciding what likes to be around water, we said that polar things like to be around water, right? Polar things like to be around water. If you are polar, what does that mean? If a molecule is polar, do you remember what polar means? Polar molecules, they've got polar covalent bonds. What's happening with my electrons in a polar covalent bond? Yeah, so polar molecules, we're talking a little bit about opposites attract, although ionic bonds are the ones that are really opposites attract. Polar molecules, let's type it up here, have polar covalent bonds. So electrons are or are not shared equally. Do we share equally in polar covalent? We're still studying our bonds, it sounds like. Yeah, polar covalent, we do not share equally. Electrons are not shared equally. If I don't share my electrons equally, I have things called dipoles. These have dipoles. Oops, dipoles. This is something we mentioned yesterday, and we need to keep processing through with our studying here. Polar molecules with those polar covalent bonds, not equal sharing. If I don't have equal sharing, I have dipoles. That's areas of partial positive or partial negative charge. Partial positive and partial negative is something that water has too. Water has dipoles. Water has dipoles. It has areas of partial positive and partial negative. So when we're talking about polar amino acids, and we said that they play nice with water, it's because they have dipoles just like water does. Water has a partial positive, the polar molecule has a partial negative, they want to be close to each other. Or water has a partial negative and the molecule partial positive, they want to be close to each other. Things with dipoles like to be close to water. Yeah, they're attracted to each other. When we talk about an amino acid that's completely negative or completely positive, not only do I have a partial positive or negative, I'm completely sold on having a charge. This is like what we talked about yesterday with ionic bonds. Remember that salt, that was our example of an ionic bond. Remember that salt loves water, because when I put salt inside water, the sodium with its positives loves to be next to the negatives in water. And the chloride with its negative loves to be next to those positives. When we talk about amino acids that have a full positive or a full negative, these definitely also want to be around water. These do want to be around water. Things that want to be by water are things that either have a complete charge, they're completely positive or completely negative, or they have a dipole. If you have some kind of charge, you want to be by water. You like to be by water. If you don't have a charge, because remember, that's what nonpolar means. Nonpolar means that I share my electrons equally. So I have no charges at all. No charges. These are going to be the ones that don't want to be by water because they have no charge at all. If you have a positive, if you have a negative, if you have a partial positive or partial negative, all of those you do want to be by water. But if you've got no charges going on, forget this, I'm pushing that away. Help me out. What questions do we have right now? I know I missed one. Yeah, Eileen says my brain hurts. Yep, we're just going to have to keep thinking through it, keep trying to talk through it. A question that I missed, that Ariel asked, she said things that are charged cannot go through the cell membrane. Only nonpolar or non-charged things. That is correct. The only kinds of things that can get through a membrane is something that has no charges, that is nonpolar, or that is hydrophobic. Yes, if you have a charge, whether you're an amino acid with a charge, or whether you're an ion, like our favorite ions to talk about, right? Sodium, or we like to talk about potassium, we like to talk about chloride. All of those guys cannot get through the membrane because they have a charge. And anything that has a dipole, which is a partial charge, can also not get through the membrane. So yes, it's all of these ideas, as much as we hate them, right? Polar and nonpolar, it applies to the membrane, it applies to our proteins, that stupid chemistry. It applies to everything that we talked about in our class, right? Makes our brain hurt. Yeah, so Mary Lou mentioned that needs to go back and look at yesterday's discussion. Absolutely. And I'll remind you guys too that there's a lot of good supplemental resources in the Unit 2 folder back from when we were on site. There's some videos there. So go check that out for this type of chemistry stuff. That'd probably be Unit 1 and Unit 2. Can we think of any other questions off the top of our head right now that you want me to address about protein structure? I still got stuff on my list for today, so. I know I just blew some minds, so that's okay. We got this weekend to look over stuff, and we got Monday morning to bring our last round of questions. So keep processing that. Keep working through that. So how do we use amino acid functional groups to predict which parts of the plasma membrane it would be located in? Yep, that's one of your learning objectives on the final exam learning objectives. I will refer you to, see if my computer will work for me here. Yes, there's one more review on Monday Eileen asked about. My computer is freaking out on me a little bit. Let me see if I can find right here. The question was, how do we use the functional groups to predict where we would find amino acids? Here is, can anyone tell me from your lecture packet, what page number is this picture on? Can anyone tell me? Okay, sounds like it's on page 5. On page 5, I ask you to do just that. I ask you to tell me which kinds of amino acids would I find in various locations. And this is going to be just like yesterday in office hours when we went through and we looked at the plasma membrane and we labeled the parts of the plasma membrane. Remember how we said, are you nonpolar or are you polar? Are you hydrophobic? Are you hydrophilic? When we talk about amino acids in the membrane, amino acids are always going to be found where they match. So let's look over here on my membrane right here. These blue parts of my proteins, I'm seeing a bunch of different shapes of proteins. These blue parts on my proteins are touching those lipid tails in the middle of my membrane here. When I talk about the lipid tails, here's our options that we just saw. We have polar amino acids, non-polar amino acids, positively charged, and negative. Oh, that's not going to work. Negatively charged amino acids. Here's our types. Excuse me. These blue ones are right next to my tails. When I talk about my tails in the plasma membrane, which of these words up here would we use to describe the lipid tails in my plasma membrane? Which words would we use to describe this part right here? Yeah, Pilar's chiming in with the 2 types of words that we use to describe it. The word from our list up here that we use to describe it is nonpolar. And remember, nonpolar means the same thing as hydrophobic. So I'm looking at a part of my membrane that is nonpolar or hydrophobic. My amino acids that live inside membrane need to be nonpolar or hydrophobic. They've got to match to be able to live inside of here. Otherwise, remember, these little tails, they'll just kick stuff out. If you don't match me, you shall not pass, and you definitely shall not live in the midst of us. You can't be here in the middle. So nonpolar amino acids live inside the membrane. They're touching those tails. When we talk about, notice here we've got labeled extracellular, the extracellular environment, or the cytoplasmic environment on the cytoplasm side. Remember from yesterday's office hours, we said that outside the cell, we've got water. And inside the cell, we've got water. So these amino acids that I see out here are going to be amino acids that need to play nice with water. Which of these types listed up here would we say play nice with water? We actually just talked about this. Who plays nice with water? Yep, so those polar ones would. Anybody else play nice with water? Or is it just the polar ones? What about these guys? Positive and negative. Yeah, if you've got a charge, you play nice with water too. So when I look at my picture here, anybody who's touching water needs to play nice with water. There's water outside, there's water inside. This purple color that I see here represents amino acids that fall into these categories. It's polar, it's positive, it's negative, because all of those would do just fine with water. All of these blue ones that I see mixed in the middle of the membrane, touching those tails, there's only one option for them. They've got to be nonpolar, because the tails that live inside the membrane are nonpolar too. So use those characteristics of the membrane. Which parts are polar? Which parts are nonpolar? Or use our discussion, where is there water or where is there not water in the middle part here. Use those as you're thinking about the types of amino acids. I promise it's basically the exact same question as what can cross the membrane. Like literally, if you go through and you look at the final exam objectives list, like it's probably 3 or 4 different ways of asking the same question. The question basically is, what kinds of things can and cannot cross the membrane? There's like a million different ways to ask that question. So here's yet another way to ask that question. Who can live on the inside? Who cannot live on the inside? It all comes down to the same kinds of things that can diffuse through the membrane and can't diffuse through the membrane. So there's a whole lot of that basic chemistry going on. I want to make sure we understand hydrophobic and hydrophilic, nonpolar and polar, those kind of things. How do we feel about those questions? You're welcome, Emily. Glad to clarify on that one. Perfect. Okay. I've got a little bit of time left, so here's what I think I'm going to do. I'm going to talk to you guys about the types of cell junctions. I'm going to use the rest of our time today to talk cell junctions, and we will talk feedback loops first thing Monday, and then bring any other topics that you guys want me to review with you on Monday. I apologize. I'm going to have to do crash course here through a bunch of slides because my computer is dying on me here. Let's see if I can get all the way to those cell junctions. All of your pretty pictures. Here we go. Cell junctions. That wasn't terrible. Okay. We are now into the integument packet. Is that packet number 7, I think? Lecture number 7. Can't remember our numbers for sure. Yeah, okay, so lecture number 7. When we talk about the skin, perfect, so we're on about page 4, perfect. When we talk about the skin, remember that your skin has 3 different layers to it. Let me bounce back a couple here, we'll get our layers. Remember that the skin has 3 different layers. We've got this outermost layer called the epidermis. We've got the biggest layer in the middle called the dermis, and then we've got that lowest layer called the hypodermis. Remember that each of these layers of the skin have different types of tissue inside of them. When we're talking about cell junctions, we're primarily talking about the way that cells of the epidermis interact with each other. So let me put some numbers here. I'll make you do a little bit of lab review here. Which of these numbers that I labeled, 1, 2, 3, or 4, which of these represents what the type of tissue in the epidermis layer of the skin? Do you remember which number would be the epidermis? Yeah, so lots of us chime in. We haven't forgotten our tissues. This up here is the epidermis layer of the skin. Now, the reason I mention that is because the epidermis layer of the skin is made entirely of cells. So here's our tissue type. I'll type it out for us. Called keratinized. Won't make you type it, right? Keratinized, stratified, squamous, epithelium. This is the type of tissue that makes up the outer layer of the skin. It is entirely made of cells. Epithelial tissue is all cells. So I've got to connect these cells to each other to make sure that I don't lose them until I'm ready to lose them, until they're here on the very outside and they're supposed to fall off. So when I look at my cells, one of the ways that I attach those cells to each other are using a type of junction called desmosomes. Desmosomes. So my first type of junction that I'm looking at right here, these junctions are called desmosomes. So desmosomes are a junction that I have between each of my types of cells of the epidermis. Hey, I'll make you do a little bit of typing. Can anyone tell me the special name of the cells in the epidermis? Do we happen to remember their special name that comes from what they're filled with? Yeah, they're filled with the protein that I see over here. This protein I see over here is called keratin. The cells are filled with keratin. So the name of these cells, big long name, keratinocytes. Keratinocytes. Desmosomes are the primary way that I anchor together my keratinocytes, my cells of the skin. The reason that matters is if you see all of these little purple lines that are coming off of, here's a desmosome right here, a way that I attach these cells together. To help that desmosome stay intact, to make sure it doesn't fall apart, we have all of these different keratin proteins that spread out in all kinds of directions to help me out with attaching my cells. See, desmosomes are the type of junction that are really good for pulling in a lot of different directions. So if this cell over here on the right gets pulled up, if it's going this way, I've got some proteins down here that are holding onto it tight. But maybe instead this cell gets pulled this direction. I've got some proteins over here that can hold it tight, or down here. So the idea is with a desmosome, there are all kinds of keratin proteins that are holding on to or helping to form this junction between the cells. This is great because if you rub your hands together, you pull those cells in all kinds of directions, and we don't want them to fall apart. So the goal of a desmosome is to hold your cells together to resist pulling in a lot of different directions. True or false? Let's make sure we remember. Desmosomes have the protein keratin in them. Desmosomes use keratin. True or false? Can we remember? Ooh. Check this out. It is actually true. My desmosomes do use keratin. All these little guys right here that I'm drawing on top of, all of these are keratin proteins. Desmosomes do use keratin. But you know who doesn't? Yes, yeah, Mary Lou's chiming in. You know who doesn't are those tight junctions. Tight junctions do not use keratin. Tight junctions do not use keratin. Here's the other type of junction that I use to hold together my cells in the epidermis, tight junctions. The goal of tight junctions is not to resist pulling in multiple directions, because that's what the keratin was good for. The keratin was helping me to pull in lots of directions, pulling all over the place. Tight junctions, they fuse the membranes of cells together. They pull them together super tight. The goal of a tight junction, especially when we're thinking about it in the skin, tight junctions keep water out. Or for that matter, they also help to keep water in, so you don't lose all your water, get really dehydrated. We have tight junctions that hold the cells together to help you not lose water. And then we have those desmosomes that we saw on the previous slide that help you with pulling to make sure the cells don't fall off. So 2 different types of junctions that I see between my epidermis cells, the ones that keep them from being pulled apart, which are the desmosomes, and the ones that fuse their membranes together, which are those tight junction proteins. By the way, let's see if any of us happen to remember this from back in the day. There's something else that my keratinocytes use to make them waterproof. What is something that the keratinocytes make that they spit out that makes them waterproof? Yeah, so their technical name, those lamellar granules, or the way that we also called them too, we called them glycolipids. The other thing that I do to keep water in and out of my skin is I use these lamellar granules, or these things called glycolipids. They also help to waterproof the skin. So when we're talking about functions of tight junctions, their function is the same thing as those lamellar granules, which is to waterproof the skin. When we talk about desmosomes, their function is to anchor those cells together really tightly to make sure they don't fall off. Yeah, so to answer your question, Mary Lou, about desmosomes, yes, desmosomes are all about pulling. If I'm pulling in different directions, let's make sure that I don't pull apart. When we talk about tight junctions, let's make sure that water doesn't get in or out. Absolutely. That is about all that I have time for today. We will talk about feedback loops on Monday. We can also talk about any other topics that you come across in your reviewing this weekend to help you out with that. Let me pop up really fast if it'll let me. Let's see if it'll let me. Okay. Reminders. We did this at the end of class yesterday, right? So here we go. Due date reminders, just to make sure it's out there. Tonight at 11:59 p.m. Remember, current events in anatomy. Hey, I've gotten several emails about whether you have to go through and do 4 different submissions, or if you can upload your 4 documents all at once. You can upload all 4 at once. I've checked that for multiple students and that works. So if you want to go through and upload 4 at once, as opposed to going through upload, submit, you can do all of them at once. That's totally fine. Remember, we must do at least 1. Can do up to 4. If you do up to 4, that means you've got 3 extra credit. 3 extra credit. I think Eileen was asking about you're doing it in 2 submissions. That's totally fine. So it's easiest for me if they're saved as different Word documents. If you happen to copy the template and put it into the same Word document 4 times, as long as it's really clear to me where each of your articles begins and ends, that's okay. But I would prefer that you save 4 separate Word documents and submit them for me either all in one submission that has 4 attachments, or do 4 different 4 different attempts, or whatever they call it. You can submit them either way. So that's tonight at 11:59. Then Sunday night at 11:59. That's that group wiki project. Group wiki project. Please make sure, if you have not already, that you're going in and you're starting to work on that. I've also gotten questions about at what point, if my group members are not contributing, at what point do I need to step up? I would say that point is probably Sunday morning, Saturday night or Sunday morning. If you've got group members you've never heard from, I apologize if it ended up that way. That would be the point that I'd say go ahead and start crafting some answers to their questions. I'll emphasize this again because I've told this to a lot of students. I can tell what work you've done on the group wiki. I can see everything that you've done. I can see if somebody goes in and tries to claim credit for the work that you've done. I can tell that. So please know that if you end up having to do more than your fair share of work, you will get the points for it and your group members won't. So group wiki project due Sunday night. I'll put here by Sunday morning. Try to have all questions answered. So that's the point, like I mentioned. If you've got some group members that are not really participating, that's the point that we would start to address that. And then the very last thing, oh my goodness, lecture final exam. Oh, exam. Oh man, that's exciting. Lecture final exam opens Monday morning at 7:30 a.m. I don't think anyone will take it that early, but it's there for you. Closes Tuesday night at 11:59 p.m. It's going to be just like exam 4, where it's one question at a time, no backtracking. So the same format that you're used to. As always, please plan to take it probably no later than Tuesday morning in case your internet freaks out on you, and that gives you some wiggle room to try to get it done. So that lecture exam due by Tuesday night. I am working through the grading, so with current events coming in tonight, I hope to do some grading of that over the weekend and then start up on Monday, Tuesday, get those group wikis graded for you. I will send out an email when your grades are finalized. So you'll get a message that tells you when your final grade in the course is posted. Eileen's asking the timing on the final exam. Since I don't know exactly how many questions it has yet, I can't tell you for sure. My guess would be, based on the writing I've done so far, plan for it to be, well, we talked about this yesterday. If you go through and count the number of learning objectives, assume there's one question per learning objective. So that's something like 75 questions, maybe less than that. So when I have more details, I will have details for you by Sunday. Obviously, you'll know by Sunday. So I'll make sure that you're aware of that. But yeah, it's not, full disclosure, it's not completely done yet. I have been working on it, but I've also been grading things. So I apologize that it's delayed. Do I have any Tuesday, Thursday friends that are in the group me? Pam, are you a Tuesday, Thursday class person? Could you make sure that this information goes out in the group me for me? Because I didn't have anyone yesterday that was in there. Thank you. Yeah, so let's just make sure we're all aware that we got stuff going on tonight, we got stuff going on Sunday, and then we're wrapping up on Monday. And here's our little fun one, right? Remember this. I got all you guys here, so we're gonna get this word out too. Monday is the last office hours. As usual, office hours 9:30 to 11:30. Bring your last minute questions, but also bring a glass of something or toast, right? I told you guys it's going to be cran grape for me, for the pregnant one over here. But bring a glass of something at the very end of our office hours together around that 11:30 time frame. Try to not look like, in the words of somebody in the chat, a feral cat, right? I would love to see your face just briefly for 10 seconds for us to raise our virtual glasses together. So get that word out. I would love to see as many of you guys as possible for one last hurrah together. I'm tearing up thinking about it, no joke. So like I legit might cry on Monday to see you all again. So get that word out to your classmates too. I'd love to see you guys briefly on Monday before we start that final exam together. So, all right, that's everything I got for today. I'm going to turn off the recording, stick around for a little bit, and then we'll call it a weekend. So goodbye to our friends on the recording.